All right, hello. I'm Dylan Wolf. This is our capstone project. This is a model power system for hands-on learning. So this is going to be a lab tool for the electrical engineering students to use in their courses. I'm not sure how well you can see it on the camera, but over there we have a bit of a flow chart of the courses at OU and then some of the key concepts that they teach. And those were our main concepts that we were trying to incorporate into this system so students could learn more about those in a lab setting. We could start from the bottom. This is a power. This is the source of our power in the system. It's a synchronous generator. It creates three-phase power, which means that there's 3 different phases of AC voltage running all at once. This is how they do it in real transmission lines. If you look at a transmission line, when you're going down the highway, you're going to see 3 lines, and then 1/4 line that's at the very top. That's a ground line. And so one of the ways that electrical engineers conserve power when they're creating transmission lines is that they step the voltage up with a transformer. What that does is reduce the current losses, which is just one of the losses that you get when you're distributing power throughout a transmission system. And then I can direct your attention over here. We have it kind of feed up into 2 main areas. So these are some of the contactors that we use to control which parts of the system are on and off. We get a, is it on the, okay. And then we have some more transformers to step things back down. So you can get the voltages that you see in your home, like 120. But here, ours are all scaled down very much further, so this is more like 35 volts instead of 120. And then we have transmission lines. So for power systems students, you learn about transmission line modeling. Here's some of the models that you'll see. These are all based on real transmission lines. We have a long one, a medium one, and a short one. And then over here we have resistors that model a residential load. So this is like your home, this is your neighborhood. And then in this section we have an industrial load modeled by a motor. Yeah, because the industrial loads tend to be more inductive. And so let's turn this thing on. It was off before because we have limit switches in here. They just open, like whenever they're open, they make sure that everything turns off for safety. Yeah, so now these resistors over here are dissipating power. Yep, now it's working. And you can see everything that's being read over here, voltages, currents, etc. And then if we switch the motor on, you can see the fan start spinning in a little bit. Sometimes it does a little dance. We're working on that part. There's a limit switch? And there we go. The world's most expensive heater. So this not only cools down the resistors that we have over here, but it also helps model the industrial load, like I was saying before. The problem with these is that they take up a lot of reactive power. Reactive power doesn't do anything for you. It's in opposition to real power. When you're making a transmission system, you want real power. So what you do in order to fix that is you have these parallel capacitors right here, and you can enable them. So I'm going to flip them in, and then you'll see the voltage and current go way up from where they were before. This is something that's unique to our system because this actually draws more power than the generator can provide. So before it was kind of simulating a brownout, but then when you power factor correct, then this pulls a little bit less apparent power, more real power. The generator is able to provide more of that. What else do we want? So right, that's a power factor correction is a great example of one of the concepts that we're trying to reinforce. Usually when students go into lab, these things are kind of abstract. You only really hear about them in models or in papers. So being able to actually see these in person should prove very useful as a lab tool for student learning. I'm going to pass it over to Jake. He's going to tell you a little bit more about the control system. Yeah, take it away.
So here is the control board for this system. So this holds all of our electronics, and it's how we get the behavior that you're seeing out of this thing. Because without this, none of our contactors turn on, none of our faults engage, nothing happens. It does nothing. And so here we have our board, and it will hold an Arduino, so that's like a little computer. We have our analog to digital converter, and that's what's actually giving us the readings, and that's how we can act upon things. That's how when we engage a fault, we see a current, and we see that it's higher than what we are expecting, and then we can act upon it, and what we do is we shut the contactors off. And so that's pretty much all there is to the control system. There's a few, like over here we have the digital side, so this is where your contactors plug into, and this is how they receive their power or their signal to turn on and off. Right here is where our voltages and currents actually come from the system into our ADC. And then right here is where the microcontroller sits. And that's about all for the control system.